Welcome to the AI Research Roundup. I am Alex. Today, we're diving into a fascinating paper from the Papers with Code trending list, published on April 26, 2025. It's called Paper2Code, Automating Code Generation from Scientific Papers in Machine Learning. So the big idea here is to tackle a common headache for researchers. You know when a great paper comes out, but there's no code to actually run it. This work introduces PaperCoder, a system that uses what's called a multi-agent LLM framework, essentially a team of specialized AI models working together to automatically turn these research papers into working code. And if you want to dive deeper, well, the authors have made the code for this work available. The repository, Paper2Code, provides their multi-agent LLM system designed to transform papers into code. And you'll find, the core codes directory, scripts to run it, examples, and even benchmark data there. Alright, so figure 1 here really sets the stage. On the left, in panel A, we see a diagram of the PaperCoder system itself. It shows how a research paper goes in, then through 3 key steps. First, planning, where the system figures out the main parts and how they connect. Second, analyzing, which involves a deeper dive into each component. And third, coding, where the actual code is generated. And the output? A complete code repository. Then, panel B drives home why this is so important. It's a bar chart showing code availability for recent top machine learning conferences in 2024, like ICLR, NeurIPS, and ICML. The blue bars are the total accepted papers, and the small orange bits at the bottom show how many of those actually came with code. For instance, at NeurIPS 2024, it's a shockingly low 10.9%. This really highlights the gap PaperCoder aims to fill. Okay, so figure 2 gives us a more detailed comparison. On the left, you see a naive approach, basically just feeding the paper to an LLM and hoping for the best. The example shows this often misses key details, like positional encoding, which helps the model understand the order of data, or even the correct optimizer. But PaperCoder on the right breaks it down much more. That planning stage we mentioned, it's not just one step. It includes creating an overall plan, designing the system architecture, like how different code modules connect, defining the logic with specific files, and even generating configuration files. These configuration files often store hyperparameters, which are like crucial settings for the AI model that are set beforehand, not learned from the data itself. Alright, so this detailed planning we were just talking about, Table 1 here really shows its impact. This table presents results on their Paper2Code benchmark, using both reference-based evaluation, which means comparing the generated code against the original author's implementation and the paper, and reference-free evaluation, which relies only on the paper to assess correctness on a 1 to 5 scale. PaperCoder, in bold, consistently outperforms other methods like ChatDev across conferences like ICML and NeurIPS. And it generates much larger repositories, more tokens, files, and functions, indicating more complete implementations. Okay, so those automated metrics are one thing, but what about human experts? Table 3 here shows us exactly that, human evaluation results. 13 of the original paper authors were asked to rank repositories generated by different methods. For comparison, the model-based evaluation scores we just saw were converted into rankings too. And again, PaperCoder, in bold, comes out on top, with the highest human scores, like 4.23 and 4.54, and the best, meaning lowest, human rankings, 1.38 and 1.23 against various baselines. This suggests that actual researchers find PaperCoder's output most helpful. So while human judgment is invaluable, it's also important to see if the automated metrics align. Figure 3 here looks at precisely that. It's a scatter plot showing the relationship between the reference-based model scores, those are on the horizontal axis, and the reference-free model scores on the vertical axis. Each blue dot is a generated code repository. You can see a clear upward trend, and the paper reports a Pearson correlation coefficient, often just called Pearson R, of 0.79. Pearson R measures how strongly two things are related. A value close to 1, like 0.79, indicates a strong positive relationship. This suggests that the reference-free evaluation, which doesn't need original code, is a pretty good substitute. Alright, so we've seen that reference-free evaluation aligns well with reference-based. Now, Table 2 here shifts to a different benchmark, the PaperBench Code-Dev benchmark, and looks at what they call replication scores. This score, as a percentage, essentially measures how well the generated code manages to replicate the core methods described in the paper. And, well, PaperCoder achieves a replication score of 44.26%, which is substantially higher than the basic agent at 5.1% or the iterative agent at 16.4%. This further underscores PaperCoder's strength in generating truly useful code. Okay, so after seeing PaperCoder's strong performance on the PaperBench Code-Dev benchmark, Figure 4 here gives us more insight from human evaluators, specifically on helpfulness and how accurately different parts of the paper are implemented. The blue bar at the top shows that 85% of authors found the generated code helpful overall. Then, looking at specific sections of a paper, the green bar shows that the core method section was implemented with 85% accuracy, which is fantastic. Evaluation code was at 70% and data processing at 48%, suggesting that while very good, there's still some room for improvement in capturing all the data handling details. With those impressive human evaluation scores, especially for implementing core methods, it really seems PaperCoder is a significant step forward. The ability to more reliably generate usable code directly from scientific papers, well, that could dramatically speed up how fast the research community can build on new discoveries, bridging that gap between publication and practical application. That's all for this AI Research Roundup. Thanks for joining me. I'm Alex.